Welcome back, everybody. I did receive the new mic today, so given it its trial run here, hopefully the audio levels are appropriate. I'm going to try to put a survey at the end of this video where you can tell me if it's too quiet or too loud, if the extra noises are really distracting. The big difference between this mic and the previous one is the old one was somewhat noise canceling, but the noise canceling also created some bad feedback sounds as well. So this should be a better sound, but you're going to hear more things in the room. You'll probably hear my wife and kids walking above me and the furnace running or the washing machine running. So if that gets to be really annoying, then let me know and we'll see if we can adjust something to make it better. Alright, so for this set of notes we're looking at vectors, and you can see from the packet it is a big one. It's 10 pages. The beginning part moves pretty fast. It's the first several objectives are pretty easy. The last objective is going to be a bit trickier. So we're going to introduce what vectors are, we're going to graph them, we're going to perform operations on them just geometrically, and then after that we will write them in what's called a position vector notation, which will allow us to do algebraic operations. We have geometric operations that correspond to then algebraic operations. We'll be doing scalar multiplication with vectors and also calculating the magnitude of a vector. We'll identify this concept of a unit vector, and then we will write vectors in algebraic form from just their direction and their magnitude. And then, like I said, the last one is the most complex. It's modeling with vectors. That means we're going to be solving word problems, physics problems mostly, using vectors. So let's go ahead and jump right in. And my pad is not responding already. Alright, there we go. Okay, so a vector is simply a quantity that has two things. It has to have magnitude and direction. So these arrows over here are representing vectors. The magnitude of the vector is simply how long it is, and then the direction is where is it pointing. So the magnitude of this vector you see here is greater than this one since it is longer, and the two vectors have different directions. So that's all there really is for a vector. Now you can think of vectors coming from geometry, and they're really built out of two things. They're built out of lines and segments. So a line is the set of all points between two endpoints, but then it extends infinitely in both directions as well. A vector will not extend infinitely in multiple directions. It's not infinite at all. It always has a finite length. So it's more related to a line segment, where it's just a bounded set of points. But the one addition that it has is it has to have a direction. So simply all we have to do is come in and put an arrow on one side of it, and then it actually becomes a vector. That was pretty bad. Still haven't gotten the pen thing down. Okay, so like I said, you put an arrow on this and you have now a vector. So the term for it is a directed line segment. You'll notice here that this notation looks like the notation we used back in geometry for a ray, but vectors and rays are different. Rays extend forever in one direction, where a vector does not. A vector does stop. It has an initial point and it has a terminal point. So it is exactly like a segment in that regard, but it has an actual direction to it. So for example, if I came back here and put the arrow on the other side, that is a different vector than the one you have here. Different directions. They have the same lengths, so they have the same magnitude, but different directions. So that's what a geometric vector is. It's just a directed line segment. The notation that we use for a vector is going to be annoying for us since we're writing things by hand, but it is a lowercase letter that would be bolded and not italicized. So you can see the two V's here are different. This is the notation for a vector. You can also put a little line segment over top of it. A lot of texts for vectors, they actually put something like this, where there is no second part to the point of the angle. So that also is vector V. And then, as a directed line segment, you could do this, but like I said, I don't like this notation because it looks like a ray. Okay, so if you have a vector that has 0 magnitude, meaning that its length is 0, we simply call that the 0 vector. And we write it as this 0 here. But you notice this is actually a bolded 0, which is going to, again, be hard to denote when you're actually writing this by hand. But this is not just a regular 0. It is the vector that is 0. So that is the number that's 0. That is the vector that's 0. They essentially behave the same way, but vectors and numbers need to be thought of as different things. Alright, now if you have two vectors, we will say they're equal whenever they have the same magnitude and the same direction. So if you look at the figure over here on the right, all three of these vectors are equal. When I say equal, I mean they are literally the same thing. In geometry, we would not say these are the same directed line segments because they represent different places on the plane. But for a vector, where it is located in the plane does not matter. The only thing that matters is its direction and its magnitude. So if I trace one of these out here, and then I move it around, that's the same vector. These are indistinguishable if you're just doing vector analysis. They are the same exact thing. They're not different, they're the same. No matter where I place this, the vector is the same as all the other ones. They're not considered to be different. So this is, I think, the concept that takes the longest to get used to when it comes to vectors. I remember struggling with this concept. I said, they can't be the same. They have different initial points, so they're not the same. But in terms of a vector, what's important for vectors, they are the same thing. So where it's located is not important, only direction and magnitude. Okay, so this is just a couple diagrams illustrating this point a little bit more. So if you look at the example A here, these are equal vectors. They are the exact same thing because they have the same direction. They have the same length as well. So they're parallel to each other. You could think of it that way, but they're also the same length, so they are equal. These two vectors are not equal. They do have the same length. I constructed them so that they're equal length, meaning equal magnitude, but they don't point in the same direction, so not equal. These two vectors, you can see that they look like they're parallel, but they're not pointing in the same direction. One is pointing up to the left and the other one is pointing down to the right. They do have the same length, but they're not equal because they're pointing in different directions. Now, this example is actually kind of a special one because they're actually pointing in exactly opposite directions. So what we will define later is we will say that v is negative w, or w is negative v. This is the negative of that vector. Same length, but pointing in the opposite direction. All right, and then the last case, these vectors are also not equal to each other because they are pointing in the same direction, but they do not have the same length. All right, so let's talk first about vector addition. So when you take two vectors and add them together, the answer, the resulting vector, is called the resultant. So the way that it works is you got two vectors here, v and w, and you want to add them together. So you take the first vector, it can be placed anywhere again, and then you take the second vector and place it so that its initial point is at the terminal point of the first vector, meaning you just kind of line them up. Follow the first vector, put the other one where the first one ended, and then wherever it lands, you connect the initial point of the first vector to the final point of the second vector, and that represents the sum. And again, they didn't have to start off in these positions. So let me try to trace these out and show you what I mean. All right, so if I take them and move them, right, I'm allowed to put them anywhere I want. It doesn't matter. If you want to add them, though, you do have to put them together. So what that means is you just, wherever this one ends, you put the initial point to the other one, and then to form the resultant vector, you simply connect from this point to that point. And that new vector represents the resultant. It's the sum of the two vectors. So we'll see this actually in practice again in just a few slides here. Okay, and then as I already mentioned, if you want to have the negative of a vector, you simply take the vector and make it go in the opposite direction, the same distance, the same length, but you just would extend this backwards so that it has the same length. This would be negative v. And again, I can move it wherever I want, so if I pull it over here, that's the same thing. It doesn't matter where this is located, it's that it has the same length and is pointing in the opposite direction. Okay, so vector addition has a lot of the same properties that we see in algebra. The first one is that vector addition is commutative, meaning v plus w is the same as w plus v. This diagram over here is actually illustrating that fact. So if we have two vectors, v and w, if we want to add them, just like I showed before, you simply kind of line them up and just make a path out of them. So here's v, and then at the end of v, you place w. The sum is this black vector you see here. If we start with w instead, I moved w back over here, so it's the same starting point, and then I put v at the end of it. If I go v plus w, I still end up at the exact same point. So it didn't matter if I do v plus w or w plus v, we end up at the same terminal point. It's the same sum either way. You'll notice that this is a parallelogram here, and that's always going to happen. So sometimes people call vector addition, they say use the parallelogram method. And the idea is you just take the two vectors and you put them end to end, and it forms a parallelogram like this, and this diagonal, the long diagonal, ends up being the sum, the resultant vector. Okay, the next property is the associative property. So this is saying if you've got three vectors to add together, the grouping that you use is not important, meaning you could add the first two vectors first and then add the third one, or you could add the second and third one first and go back and add the first one. And that's what this picture is actually showing. So if we follow the blue path here, we do u plus v, which is what it says here, u plus v, and then we add on w, we end up at this point. So the solution to that, adding the three vectors for this, is this red vector that you see here. That represents the left-hand side. Okay, then if we follow, so actually they did not follow that order there. They actually followed this. So it doesn't matter, but so if we add u plus v together first, that's this black one. So this represents that sum. And then if you add w onto it, it's actually following this path for what they have in the parentheses here. And then the other way was add the v plus w first. V plus w, if we add those two together, it's this black vector here. And then if we add u on at the beginning, so u plus v plus w, we still end up at the same point at the end. So that picture illustrating the associative property. All right, I should mention the additive identity property should be pretty obvious. If you take a vector and you add nothing to it, you're going to get the same vector back. And then also, if you take a vector and add the opposite of the vector, you should get 0. So just to illustrate that, let's come back to where I had the negative vectors drawn. So the idea is when you add vectors, you're supposed to, wherever this one ends, you're supposed to start with the other vector. So if I actually put this on the ending point, the idea is you start at this point here, you'd go to this point, and then it would map you right back onto this point. Go from here to here, and then right back here. So in essence, the answer is just this point, which means it's the 0 vector. It doesn't go anywhere. Okay, so then vector subtraction. How are we going to handle vector subtraction? Well, it turns out we do the same exact thing that we do for regular numbers. If I want to take 3 minus 5, we recognize that to be the same as 3 plus a negative 5. You add the additive inverse. We do the same thing with vectors. So if I want to do vector v minus w, it's the same as doing v plus the opposite of w. So over here I have vector v, and then I added on w. So if I were to connect these two, this actually represents v plus w. Go v, and then go w. The resultant is v plus w. But that's not what we wanted here. We wanted v minus w. So at the end, if this is w, minus w, or negative w, would go in this direction, be the exact same length. These would have the same length as each other, but pointing in the opposite direction. So if I want to add these two, then going v, then negative w, this would be that resultant. meaning the red line that you see there could be represented as v plus negative w, which we said we're defining to be v minus w. Now you can actually show all of that in this same diagram that we actually had before. The one that we had for just vector addition had this diagonal that you see here. So if I do w plus v, I get this vector, or if I do v plus negative w, I still get that same vector. But this also illustrates the subtraction as well. So I want to try to show one way of showing that at least. So what I want to do is I want to put negative w at this point. So to do that, I would have to copy this. So let's do that. Man, tracing this out is not easy. Let's try that again. Not sure why I'm struggling with this. Okay, and then let's move it. So if I put this, I'm allowed to put it wherever I want. If I put it here, then let's label it. This is negative w. So I'm going to do v plus negative w, meaning I just need to connect these two. So let's actually do that in pink. So from here to here. So that vector actually represents v minus w. But remember, vectors can be placed anywhere, so that matches up exactly with this diagonal that you see here. So this is where you get the complete parallelogram representation for vector addition and vector subtraction. The longer diagonal is vector addition, and the shorter diagonal is going to be vector subtraction. Okay, the other operations that we can perform on vectors are scalar multiplication. So scalars is just another way of saying a number. Vectors are not numbers. Right? Vectors are a directed line segment. Scalar is just a regular number. It's not considered to be a vector. So we can take a scalar, like 2, and multiply it by a vector. And what that will do is it will scale up or scale down the size of the vector, meaning it's going to change its length. So if we started with vector v, if I want it to be twice as long, you basically just count out the vector. Kind of think of it almost like slope. So this is up 2 over 3. That right there would be the same as vector v, but I want to do it one more time. So up 2 over 3 a second time. That's 2v. We can also multiply by negative numbers. If you multiply by a negative number, it just reverses the direction. So if this is v, the negative 1 times v is going to have the same length, but it is pointing in the reverse direction. If you take the scalar 0 and you multiply it by a vector, then obviously you're going to get the 0 vector. Okay, so then there's lots of properties for scalars, and basically these just say that scalar multiplication behaves nicely. So the idea being, obviously 0 times a vector is 0, 1 times a vector is going to be the same thing, negative 1 times the vector is going to give you the negative vector, and then we have some distributive properties. So what this says is that you can distribute the vector over scalar addition. This would be scalar addition because you're adding two scalars together. So vector can be distributed across scalar addition, and then also a scalar can be distributed across vector addition. Both properties are true. They're actually separate from each other, but they're both true. And then this last one is kind of an associative property. So it's saying if you've got a scalar times a vector that's multiplied by another scalar, you can just go ahead and multiply the two scalars first and then multiply it by the vector, which is, what we would basically expect to be true. Okay, so let's actually start doing some of this vector addition and subtraction. So let's start with v minus w. So I've got the vectors sitting over here. Let's change back to blue. So the first thing I need is v in order to do this. And what I'm going to be drawing right now is not actually the final answer. This is just the work that we use to get the answer. So I'm going to copy v. V goes over 3 up 2. So it goes to the right 3 and then up 2. So here's v. And then if I put w in, technically we don't need w, but w goes down to over 2. So that would be to this point. All right, I'm going to come back and label these. This is v, w. But I don't need w, I need the opposite of w. So we're going to do that. Let's actually use green here. It's going to be the same length as this, so we need to go up 2, back 2, so to this point here. So that's negative w. All right, so the problem is telling us to do v plus the opposite of w. So we're adding the blue and the green vectors together. We've already got them lined up end to end, so following v and then following negative w takes us from this point to that point. Right? That's the end result of that path is the way to think about it. If you followed that path, the end result would be going from here directly to here. So the resultant vector, our answer, is just the black vector that I've drawn here. That is v minus w. And technically, that's really all that should be shown. If we ever actually get back to school and have a test over this, then I would want to see this as your work to prove to me how you're getting it, but the actual solution is just that vector. And it could be drawn anywhere. You know, I have it here, but remember, vectors can be moved anywhere on the page. So, you know, if I put it over here, it's still the same vector. Okay, so that's vector subtraction. So let's try some scalar multiplication. Now on this one, to get it to come out nicely, I have given you a starting point because it barely fits in this grid. So if I had it starting up here, we would run off the grid. So this is just as a suggestion of where to start. So it says to do 2v. So v goes over 3 up 2. So I need to do twice that. I need to go, I'm going to actually just do it step by step. It's easier rather than counting all the blocks. So I'm going to go over 3 up 2. That's not where I stop though. I have to do it a second time, over 3 up 2. So this vector is 2v. Now we're adding on to that 3w. So we're going to do the same thing, but we're going to do w 3 times. So down 2 over 2 from the endpoint of this one, down 2 over 2, and then down 2 over 2. So this vector, hopefully I can actually draw a straight line. All right, that is 3w. So then our resultant vector, the answer, is found by just connecting this initial point to this terminal point here. I don't think I trust myself, so let's see if I can get the straight edge. I haven't tried this before, so this might not go well. All right, so this is our resultant vector. So this is the vector 2v plus 3w. It's just the black one. All right, try one more here. So this one has 3 different pieces. We've got 2v minus w plus u. So we'll start with 2v. So again, we're copying that one. So over 3 up 2, over 3 up 2. So there's our 2v. We're going to subtract w. Now, w normally goes down 2 to the right 2. We need to do the opposite. So we're going to go up 2, back 2. So this is negative w. And then we're adding u onto that. So just a single u. So u goes over 1 up 3, I believe. So then we connect these. So that's our u, and this was our v. The resultant vector is just the final result of this path, meaning go here, here, here. So we start here, and we end there. So again, let's try this. Since I can't really draw straight lines. So that vector would be our resultant vector. This is 2v minus w plus u. Now the way to interpret this, like what are we actually doing here, is these vectors are going to represent forces. So they can also represent velocities of things. So for example, if you're driving in this direction, but the wind is blowing you in this direction, and then, I don't know, maybe something else is impacting you. You're going down a hill or something, it's giving you some extra force in this direction. The resulting force of all those put together would be this direction here. So we will see examples of that when we get to the modeling. Okay, so we've done some vector operations. The next thing to look at is the magnitude of a vector. The magnitude of a vector is denoted by this double absolute value symbol here, and it behaves a lot like absolute value. They're doing the same basic type of thing. The magnitude of a vector is simply the length of the vector. So this is related to what we did with complex numbers as well. With a complex number, we had a modulus. The modulus of the complex number was the distance from 0, and this is kind of the same type of thing. It's just the length of the directed line segment. So some properties, obviously the magnitude is always greater than or equal to 0. It's a distance, it's a length, so it should always be greater than or equal to 0. The only way it is 0 is if the vector itself is the 0 vector. If you take the magnitude of negative v, it's going to be the same as the magnitude of v. And then the last one here says if you have scalar multiplication on a vector, something like, let's say you have 2 times v, then you can actually apply the absolute value to the scalar and then just take the magnitude of the vector itself and multiply those together. All of those I think should be pretty obvious properties. Now, once we have this definition of magnitude, then one of the important types of vectors that they're going to deal with are vectors that have a length of 1. So if a vector has length 1, we just call it a unit vector. Okay, so we performed operations on vectors geometrically, but that's not going to be a real precise thing in general. Those all worked out nicely just because the vectors laid out nicely on grid points, and that doesn't have to be the case. So we need an algebraic way of representing vectors so that then we can define the operations algebraically. So to do that, we have this concept of a position vector. So a position vector is simply a vector that is placed in the xy plane so that its initial point is at the origin and then its terminal point is wherever it ends up. Now remember that vectors can be placed anywhere. So this vector that's given, if I trace it and I move it somewhere else, same vector, right? This is the same vector as this. So what that means is any given vector, no matter where it's located, it has a representation as a position vector. You can, in a sense, just translate it back to the origin here. It's the same vector, it's not different, has the same direction, same magnitude, so they're the same thing. So even if it's located out here, you can always just think of it as being located at the origin. Now, once it's placed at the origin, the only important things about the vector, the things that define it, are the coordinates of this terminal point, because the initial point's always the origin. So really, if we just pay attention to the coordinates of this point P, they tell us exactly what the vector looks like. So these are called the components of the vectors. And the notation that we use for an algebraic vector are these angle symbols, not parentheses. These is left angle, right angle. That's one way of denoting an algebraic vector. We're going to see a different way a little bit later on. Okay, so if you have a vector, like we do here, that's just sitting out here in the coordinate plane, and suppose you know the initial point and the terminal point, and you want to represent it as a position vector. These two vectors are the same thing. They have the same length and the same direction, but we only, let's say, are given these coordinates, and we want to figure out, well, what's A and what's B? Well, the easy way to do that is to simply take the terminal point coordinates and then subtract the initial point coordinate, meaning that A is simply equal to x2 minus x1. x2 minus x1 is the length of this segment here. And that directed line segment has to be the exact same one that's here. So A has to be equal to, this has to be equal to that expression there. All right, the difference in the x's is the length of A. Same thing with the y. The difference in the y's has to be this length here, which is B. So this enables us to immediately take any vector, any directed line segment in the coordinate plane, and convert it into a position vector. Okay, so let's actually do that with this example here. So this vector is just a general vector in the coordinate plane. We have our initial point and a terminal point, and we want to place it here at the origin. So to do that, we need to figure out the a, and a will be x2 minus x1. And order does matter here. You have to do the ending minus the beginning. So in this case, this is the ending. 4 is the x2, and -1 is the x1. So that's going to be 4 minus a -1, which comes out as 5. And then the b, same thing, y2 minus y1. y2 is 6. y1 is 2. So we get 4. So our vector, written as a position vector, is 5, 4. And that's all there is to it. Now, just to show you that this is actually valid, if we come over here and plot it, a position vector always starts at the origin, and then we just plot the terminal point, so over 5, up 4. So if we connect these two, you know what, I better use my straight edge again. And if I take that, I don't think it'll take the arrowhead with it, but we'll see. No, it doesn't. But you can see if I bring it up here, they have the same length and the same direction. So these two vectors are actually identical. This is it as a position vector, and this is just at a random place in the coordinate plane. But they are considered to be the same vector, and this is just a more convenient way of representing that vector. It has all the important information that we'll be able to figure out what its direction is and what its length is just from this form here. Alright, now this enables us to determine if two vectors are actually equal to each other. So since every vector can be written as a position vector, take the two vectors that you have, v and w, if you want to know if they're equal, represent them as position vectors. Once they're written as position vectors, the only way they're equal is if these coordinates are exactly these coordinates. So pretty easy. Just make them position vectors and see if they have the same numbers. Okay, now, as with everything in math, we like to do all of our different operations in many different ways. So the notation that we just showed you for representing a position vector, it's not the only way to represent them. Another way to represent it is to use what are called basis vectors, or they're technically unit vectors. They're special unit vectors, and it's just a different way of representing it. It has some benefits over this form, so you just need to be exposed to each one. So the vector I, not to be confused with the imaginary constant. I know it's unfortunate. We use the same thing for square root of -1. This is not that I, it's the vector I, is the position vector 1, 0. So it just represents the vector along the x-axis that is 1 unit long. The vector j, similarly, it's a unit vector, but it's along the y-axis. The idea is that any vector that you have, pick any vector you want, it can be expressed as a linear combination of these two vectors, meaning that you just have to multiply this by something, and add it together to represent this vector. And that's what this is actually telling you. If you take some number, multiply it by I, that'll scale this vector up or scale it down, and then do the same thing with b, scale it up or scale it down, add the two together, and the resultant vector would be the one that you see here. Right? If we call this endpoint, let's say, is AB, then the vector that is right here that I've just drawn in would be A times the vector I, and then this one, just slightly higher, this would be B times J. And if you add those two together, then you get this vector that you see here. So as written in the form before, that would be the position form, and then you also could write it as AI plus B times J. The confusing thing here is that A and B are scalars, I and J are vectors. So you have to keep that straight. We call the A part the horizontal component, and then this is the vertical component. Right, the A is the horizontal and the B is the vertical. Okay, now once we have these representations, whether you use the unit vector representation or the position vector representation, we can now define the algebraic operations. And they're exactly what you'd expect them to be. If you want to add two vectors, you simply add their horizontal components together and you add their vertical components together, and that's it. Right, if this is the representation, oh, there's a typo, that should be a 1 there. Hopefully that's fixed in your notes. Update that if it's not. Let's see if it's fixed on mine. Okay, it looks like, no, that's not it. Yeah, it looks like I fixed it in yours. Should be at 1 there as well. Okay, so if we want to add this vector to this vector, you simply add the horizontal components, a1 plus a2, and then add the vertical components, b1 plus b2. Subtraction, going to work the same way. Subtract the vertical components, or keep saying it backwards. Subtract the horizontal components and subtract the vertical components. Scalar multiplication, you just multiply the scalar by each of the components, exactly what you'd expect it to be. And then finally, this gives us the ability to calculate the magnitude of a vector as well. And this should have been pretty obvious, but if this is, if you just have, let's just draw a single vector here. So let's say it is the vector AB, then this horizontal distance is A, vertical distance is B. The length of the vector can be found using Pythagorean theorem. So that's where this is coming from. So magnitude is just Pythagorean theorem. Just like the modulus was Pythagorean theorem for complex numbers. Okay, so these pictures are just illustrating. There's the picture I needed for distance formula. So I don't think we need to dwell on those. So let's actually just do the math. So these are the ones that are, they're really just dead simple. They work exactly as you'd expect it. So I have my vector v, I have a vector w, written in both forms. If you want to add them together, I'm going to start with the position form. It would simply be 2 plus 3 for the horizontal component and 3 minus 4 for the vertical component, which gives you the vector of 5, negative 1. So that's written in position form. I believe most of the problems on Math Excel are going to have you write it in this form. So that would be 5i minus just a j. Right, we can go ahead and put that as the coefficient. We don't really have to write the 1 there. So that is the resultant vector you get by adding these two vectors together. So either form's acceptable, but I think that's what they're going to have on Math Excel. All right, v minus w works the same way. So horizontal components, 2 minus 3. Vertical components, 3 minus a negative 4. So we end up with negative 1, 7. So that is negative I plus 7j. All right, so easy. Vector addition, vector subtraction, very easy. Okay, so scalar multiplication, also very easy. If we're going to take 3 times v, we just multiply these components by the 3. So 3v is 6, 9. Just multiply 2 and 3 by 3. If you want to write it in the other form, then that's 6i plus 9j. All right, so now we have scalar multiplication with vector subtraction. So let's do the multiplication first. So the multiplication for 2v, we're going to have 4, 6 minus 3 times w. So 3 times w is going to be 9, negative 12. And then when you subtract, we're going to have negative 5. Oh, sorry. Yes, sorry. Let's actually go slower. Make sure I don't lose you here. All right, so the components, it'll be 4 minus 9, and then 6, be careful here, minus a negative 12. So we end up with negative 5, 18. and then written in the other form would be negative 5i plus 18j. Okay, and then the last one, to find the magnitude, all we need to do is Pythagorean theorem. So magnitude, this is also called the norm. So if you hear me say the norm of the vector, that is the same thing as the magnitude. Okay, so we're doing vector v, so this one here, so that's going to be square root of 2 squared plus 3 squared. So that is square root of 4 plus 9, or square root of 13. Alright, so that's all there is for the vector operations. Pretty easy. So next thing we want to look at is unit vectors. Unit vectors are really convenient. We'll use them extensively when it comes to modeling problems. It's just convenient to have a length of 1. So that's, remember, all a unit vector is a vector whose length is 1. Now, if you have any vector, suppose I just give you a random vector v, like this vector here, sometimes the only thing you care about the vector is its direction, and you really would prefer its length to be 1 because of other computations you might want to be doing with it. So if you want to convert a given vector v into a unit vector, all you have to do is divide it by its length, meaning divide it by its magnitude. It will have the same direction, but it will have length 1. So this is an important fact that I kind of skipped over earlier. When you do scalar multiplication, when you take a number and you multiply it by a vector, it does not change the direction of the vector. So the same thing is going to be true if I divide by a number. Could that be the equivalent to multiplying by 1 over the number, right? That is the vector over alpha. This does not change the direction of the vector. It just scales it up or scales it down. Okay, so this is actually a theorem. We should actually prove it, and the proof is written out here. I'll let you read that when you feel up to it. Let's try using it. Oh, another important fact too. This theorem, we could reorder this. We could multiply both sides by the norm or the magnitude of v, and it would give you this formula here. So what this is showing is that every vector has an alternate representation. It can be represented as its magnitude, its length, multiplied by a unit vector. And this turns out to be the #1 way that we will represent vectors in the future. We're going to have a way of quickly getting this unit vector, and then the magnitude is typically given to you. On a lot of problems, they tell you the magnitude, because most of these are forces, so they're going to tell you what the force is, which is going to be its magnitude. Okay, so let's actually apply that. We want a unit vector in the same direction as this vector here. So the formula says that the unit vector will be v divided by its magnitude. So let's start by just finding the magnitude. If you look at the components here, remember this is the vector 4, -3. Should actually be pretty obvious what the magnitude is, but let's just put it in the formula. So it's square root of 4 squared minus -3 squared. So that is square root of 16. Oh, this is not minus, that's plus. Plus 9, which is square root of 25, which is 5. All right, the reason it should have been obvious is if you plot this point out, this is a 3, 4, 5 right triangle. So its magnitude is 5. So now all we have to do is take v and divide it by 5. Well, if we write v using this form, to divide it by 5, you just divide each component by 5. So there's our unit vector. Again, chances are MathXL is going to make you write it with the basis notation, the I and the J. So probably going to go with that. And that's it. That's all there is to it. Pretty easy again. Okay, so as I mentioned, a lot of times in the problems that we're going to be dealing with, the vector is either going to represent velocity or it's going to represent some kind of force. In both of these situations, you typically are given the actual velocity and the direction that it's flowing, meaning that you're given the magnitude of the vector and you're given the direction of the vector. You're not typically given horizontal and vertical components. It's just not how we typically think about vectors. If the velocity vector is representing the wind, then we would say how fast the wind is moving and in what direction. The speed of the wind would be its magnitude of the velocity vector, and the direction, obviously, of the wind is the direction of the vector. So we want to take a vector, that is in the normal form. We have the horizontal and vertical components, and we want to represent it using just magnitude and direction. So this is where what we were doing with polar coordinates comes in. So here's my vector. Okay, this is the vector ai plus b times j, and it has some direction. The direction is going to be represented with theta here, and then the magnitude is just the denoted by this notation here. So if we turn this into a triangle, like we do with just about everything, the horizontal component here would be a, and the vertical component would be b. Right? Obviously, a is a negative number in this case, but since it is a right triangle here, we could use trigonometry. If we do the cosine of theta is going to be the x value divided by the radius, x over radius. If we multiply the radius, which in this case is the magnitude, to the other side, it gives us a formula for a. A is really the magnitude of the vector multiplied by cosine of theta. In other words, the horizontal component can be expressed solely as a product of the magnitude and the direction. Theta was direction, then this is the magnitude. We can do the same type of thing for the the vertical component. If we do sine of theta is going to be the y value divided by the radius. Multiply that to the other side, and we get an expression for the b. The vertical component is the magnitude of the vector times sine theta. So now if we come back to this representation, we can just plug in these expressions. So we're just replacing a by the magnitude of v times cosine theta and replacing the b by its corresponding expression. So this is literally saying the exact same thing as this. They look different, but same thing. All right, the final thing that we typically do is we go ahead and just pull the magnitude of v out. This looks exactly like what we did with complex numbers. So with a complex number, we said you put its magnitude out in front, and then inside you had cosine theta plus sine theta, or I think we had I here. Now this I and that I do not represent the same thing. Remember, this is a vector, where this is the square root of -1, but the overall structure, it is doing basically the exact same thing. Complex numbers in the complex plane can actually be thought of as vectors. They really are the same exact type of object. So that's where this symmetry is coming from. We are really describing the same type of thing as what we did before. Okay, now the other thing to notice, and I think this is on the next slide, but this actually could be thought of as a vector, the magnitude of a vector multiplied by a unit vector. This vector here, this thing is a vector. It's just a number times the vector I plus a number times the vector j. It is a vector of length 1 because these represent points on a unit circle. So let's see if that's on the next slide. Okay, not yet. Must be the one after this. So this is just restating it again. So anytime you are just given a vector, you're given its direction and you're given its magnitude, you can immediately write down what the vector is in this form here. And then if you evaluate this, it can be converted into this form. Okay, this is the slide I was talking about. So if we think all the way back to when we defined the trigonometric ratios, we said that you have a circle of radius 1 and you put a point on that circle. The x coordinate of that point is cosine theta and the y coordinate is sine theta. So if we connect that and make a directed line segment here, this would be this vector that you see here. And that vector has to have a length of 1. The magnitude of that vector has to be 1 because it's the same as the radius of the circle. So that's showing us that this representation is actually showing the vector as its magnitude multiplied by a unit vector. This is always a unit vector of length 1. So that's all this is saying. It's a unit vector that has the same direction as the given vector. Okay, so let's try solving an application problem. Okay, so it says a ball is thrown with an initial speed of 25 miles per hour in a direction that makes a 30-degree angle with the positive x-axis. Express the velocity vector v in terms of I and j. Then, what is the initial speed in the horizontal direction, and what is the initial speed in the vertical direction? So let's start by just trying to get the vector. So I've represented it in the xy plane here. This is our vector. It said that the initial speed was 25 miles per hour. That is the magnitude of the vector, right? The 25 is the magnitude of v. And then it said that the direction is in a 30-degree angle with the positive x-axis. So that's why this angle here is 30 degrees. Okay, so let's make sure we write that down. Magnitude was 25, and then the direction is obviously given to be 30. So we can go directly into this form. V has to be the vector 25 multiplied by cosine of 30i. And I don't like writing it this way, but this is how the book does it. This I is not in cosine. It is outside of the cosine. So really we should have parentheses here and here, but it just gets to be too many parentheses. So that is a vector. It is outside. It is not inside of the cosine. Right? It's completely outside. Okay, plus sine of 30 times j. And again, j is not inside sine. It's outside of it. All right, so this is our vector. But they want us to write it in a more standard form, meaning they want us to write it in this form here, which means we have to go ahead and find a and b. So luckily these are nice trig ratios, so we can easily do this. So if it's a 30-degree angle, cosine is going to be square root of 3 over 2, and then sine is going to be 1/2. Okay, and then we just distribute the 25 through, so 25 square root of 3 over 2i plus 25 over 2j. If you wanted to write it in the other form, which I'm fairly certain they will not, but it would just be this. So this is the position vector representation for the vector described in the problem. You can see that this is nice for doing algebraic computations, but it doesn't describe the vector very clearly. The original description was much clearer. A vector of length 25, rotated 30 degrees from the x-axis. Much more clear representation than this is. Okay, so the last part says, what's the initial speed in the horizontal direction? So I'm going to abbreviate this initial speed in horizontal direction. That's simply the a value, meaning it's the length of this vector here. Right? One of the things that's nice about this representation is it's showing two vectors. There is a vector here, which is this one. Right? It has this as its magnitude, and then the I tells you the direction. So the length of that is the 25 radical 3 over 2. So that is the initial speed in this direction. So the idea is the ball is following this path. If you want to think of it as like this being the ground, and let's say the sun is directly over top, so that means the shadow is going perpendicular down to the ground, the shadow would have its own speed. And the speed that the shadow is moving is the same as the length of this vector. So the initial speed on the horizontal distance is 25 square root of 3 over 2, which comes out approximately to, I believe, 21.65 miles per hour. Okay, and then to do the initial speed for the vertical distance, or vertical direction, that is just the b value, meaning it's the length of this vector. This 25 over 2j is that vector. That is 25 over 2j, just like this was 25 radical 3 over 2i. That one is 25 radical 2j. And the length of that vector is just the coefficient. So vertically, it is moving at about 12.5 miles per hour. All right, that's all they were asking for us to do on that one. Okay, next problem. They gave us an algebraic form for the vector, and they want us to find the direction. So first thing I would do is make a rough sketch of it. If the horizontal component is 4, we would have to go 4 to the right. The vertical component is -4, go down 4. So this blue vector is the one that's given to us. The direction is going to be this angle here. Now this is another one of those things where they're making an arbitrary choice here. The direction does not have to be the angle alpha. It could be this angle, but our book tries to stick with angles between 0 and 2 pi, even though it doesn't have to. So we're going to actually start by finding this. So to find that angle, that's not very straight. Okay, think of this as a right triangle here, and you could use any of the trig ratios that you want. So I think probably the easiest one, though, is going to be to do tan inverse. So theta is going to be tan inverse of the y, which is -4 over 4. In other words, it is tan inverse of -1. This one we should know. Should be pretty obvious from the picture as well. This is an isosceles right triangle, which means that angle has to be -pi over 4 radians, or -45 degrees. Most of the problems are probably going to want the answers in degrees for this. Okay, so that does describe the direction of the vector, but if we want alpha, then we're going to need to do 2 pi, or I guess 360, take away the 45. So we get a direction of 315 degrees. Okay, so that's all for that one. Alright, now we get to the tricky ones. Okay, so in a problem, this is not a problem yet, I'm just kind of explaining how we're going to handle these. So if you have two forces, F sub 1 and F sub 2, and they're simultaneously acting on an object. So for example, a common one that we're going to see is in aviation. If you have a plane flying in this direction, but the wind is blowing in this direction, then both forces are acting on the actual body of the plane. And so the idea is you're going to keep moving along this path, but the wind is going to keep pushing you along this path. So taken together, the actual flight of the actual path the plane will travel will be the resultant vector. It'll be the sum of those two forces. So the as the plane's going along this vector, it's getting pushed up and up and up by the wind, so it actually ends up over here. So that's how we will represent this. If we have multiple forces acting on an object, we simply do the sum of the vectors to kind of figure out what the path is for that object. Okay, so in our first example, we've got a Boeing 737. It's maintaining a constant airspeed of 500 miles per hour, and it's headed due south. However, the jet stream is blowing 80 miles per hour in the northeasterly direction. So for the first part of this, we're supposed to express the velocity of the airplane, which we're calling v sub a, relative to the air, and then also relative form the velocity that is for the wind, the air velocity. And we're doing that in terms of I and j. Okay, so to do that, I've already made an xy plane here, just to make the position vectors easy. And since the plane is flying south, this is going to be the vector representing the plane. And the thing that we're given at the beginning is we're given the speed of the plane. So the length of this vector has to be the speed of the plane, has to be 500. We're also given the direction. The direction of the plane is due south, so that's how I was able to just draw it down here. Now, to make sure that this has the appropriate length, a length of 500, that's why it's stopping at -500 on the y-axis. So if we're going to write down what the actual formula is for VA, well, it's pretty easy. We don't have to do the whole angle thing. We can just immediately see where this terminal point is. So we could write it in this form. The x component is 0. The y component would be -500. but they want it in terms of I and j, so this would be 0i minus 500j. And we typically just drop this. Since 0 times I is 0, we would just write it as negative 500j. Okay, so that's the velocity of the aircraft. Now let's do the velocity of the wind. So for this one, we are given, again, the magnitude. The velocity is 80 miles per hour. And we're also given its direction. So its direction is northeasterly. So we're supposed to assume that that's kind of splitting this in half. Northeasterly would be dividing this in a 45-degree angle. So that's really telling us that theta for this velocity vector is 45 degrees. Okay, so that means we can go to the formula now. So again, the formula is this. And we have all the components for it. We know the magnitude is 80, and then cosine of 45 I plus sine of 45j. All right, and we can simplify it. So this is square root of 2 over 2i plus square root of 2 over 2j. And then distributing, we end up with 40 square root of 2i plus 40 square root of 2j. Alright, so we have the vector for the wind, and somewhere up here we had the vector for, oh, here it is. So this was the vector for the aircraft. Alright, that's all they asked for on part A. So let's move on to part B. Okay, now it says find the velocity vector of the 737 relative to the ground. So the point of this is that the wind is actually slowing us down. It's not a headwind, it's not directly pushing us back, but it is pushing us to the side. So even though we're trying to fly due south, we're actually going to be following more of this path here. And where that's coming from is that we need to do the resultant vector, meaning that the velocity with respect to the ground is going to be the velocity of the aircraft plus the velocity of the wind. So let's do it geometrically first, and then we can do it algebraically. So if this is the wind vector, remember that vectors can be placed anywhere. So if I take that vector and then we move it, we can place it at the end of this vector here, the end of the aircraft vector. The resultant vector is just by following the path. Go down this one and then follow here, and we connect from the initial point to the terminal point. So that's where we're getting the velocity vector for with respect to the ground. Now, mathematically, all we have to do is just add the previous vectors. So if we recall, the vector for the aircraft was just negative 500j, and then the vector for the wind was 40 square root of 2i plus 40 square root of 2j. So you just treat it like an algebra problem. We just put the j terms together and the I terms together, so you get 40 square root of 2i plus 40 square root of 2 minus 500j. And that's it. It's not very pretty, but it does represent the velocity with respect to the ground. Okay, and that's all they're asking for in part B. All right, this leads us to part C. So now it says find the actual speed and direction of the 737 relative to the ground. How fast is it actually flying? Right, through the air, as the air passes over the plane, it is traveling 500 miles per hour, but that's not going to end up being the same speed on the ground. So airspeed and ground speed are different because of the impact of the wind. So to figure out the ground speed, we simply need the magnitude of this vector. So magnitude of the vector with respect to the ground. Now remember, magnitude of a vector is simply square root of a squared plus b squared. So we just got to plug all that stuff into that expression. So the a, if we go back, a would be this, and this is b. Right? That's our a. That's our b. All right, so we end up with 40 square root of 2 all squared plus 40 square root of 2 minus 500 all squared. All right, you should be able to put that whole thing in the calculator. I wouldn't simplify it. I would just plug it right in there, and you should get approximately 447 miles per hour. So we lost about 3 miles, well, way more than 3, 53. We lost about 53 miles per hour from the impact of the wind, and we're also moved off course. So we want to find the direction. So the direction, we're going to represent it with this angle here, but in order to find that angle, we're actually going to find this one. So let's call that one theta, and then our answer will actually be this angle here. So again, to get that angle, you can think of this as a big skinny right triangle there. So we can do tan inverse again to get this angle. So theta is going to be tan inverse of the y value for this point divided by the x value. So the y value is the b, so really it's b over the a. Right? That's the y distance, this is the x distance. So it's going to be this divided by that inside tan inverse. Okay, so basically the same type of computation we did before. That comes out approximately, not exact, approximately to negative 82.7 degrees. But we don't really want that angle. We want this one because we're going to write the final answer as a bearing. So to get that angle, we would just take the complement of this. So we'll call that angle alpha, the one that we're looking for. Alpha is going to be 90 minus 82.7 degrees, and that comes out to 7.3 degrees. Okay, so as a bearing, the way to describe this is we start facing south, and then we turn 7.3 degrees towards the east. So the way we should write the direction is south, 7.3 degrees east. Start facing south and then turn 7.3 degrees towards the east. So that's our direction. This is our ground speed, and we're moving in this direction. We're no longer moving due south. The wind has pushed us off. It's south 7.3 degrees east. Okay, let's try another one. We got 2 more applications left. This is going on long, so hopefully it doesn't take too long here. These are the most challenging ones, though. So it is definitely important to take your time with this one, really try to understand the idea here. Okay, we have 2 movers. It says 2 movers are require a magnitude force of 300 pounds to push a piano up a ramp. The ramp is inclined at 20 degrees from a horizontal. And the question is, how much does the piano actually weigh? Okay, so this is a classic type of problem, and technically the way that it's written is not quite crystal clear. The way you're really supposed to interpret this 300 pounds is that it requires 300 pounds to just keep the piano stationary. If you apply 301 pounds of force, then it will start to move up. If you only apply 299 pounds, the piano will start to roll back. So really the way to interpret the 300 pounds is that is what is required to keep it stationary. Okay, so we've got the piano placed on this ramp. Now, the force of gravity is going to be perpendicular to the ground. So this F1 is representing the force of gravity. So that's what I have labeled here. F1 is the force of gravity. If we want to know the weight of the piano, then that is simply the magnitude of the force of gravity. In other words, the length of this vector is the weight of the piano. Okay, so then what are the other vectors? Well, the other vectors, you see F2 here. You could place this vector actually up here. Imagine it being the same exact length. So this vector is representing the force required to push it up. Now this is the important part here, that technically the piano's not moving. So there is another force coming backwards, right? The piano is trying to slide down the ramp, right? That's the force of gravity is trying to pull it down the ramp. And so the idea is that these two vectors are actually canceling each other out. The force at which they're pushing it up and the force at which it's being pulled down are in equilibrium. So we actually already know the magnitude of this vector. This vector is the one that you see here, and its magnitude is 300. So that's what it says. F2 is the force required to move the piano up the ramp. Technically, it's the force to keep it stationary on the ramp. We were given the magnitude of that. Magnitude of F2 is 300. Okay, and then the final vector, F3, there's two ways to think about this one as well. But one way to think about it is that it is the force of the vector, force of the piano pushing against the ramp. Since the ramp is on an incline, it is not actually pressing down with its full force. Its full force is being split up. Part of it is being pulled in this direction, and part of it is being pushed against the ramp. So the F3 is how much pressure is actually on the ramp itself. You could see this same type of phenomenon if you take like a bathroom scale and you place it on a ramp, and you stand on it. Your weight should actually be different than if it's just on the flat ground. Now there is some surface tension forces in there that kind of mess that up, but in theory that's what would happen. Placing the scale on a ramp should give you a different value than if it's just on horizontal ground. Okay, so that's all the given information. So again, the goal is we need to find the magnitude of this vector. So the illustration that you see here is just the same as this one, just blown up a little bit bigger, easier for us to write on here. So the goal is to find the length of this. And we already know the length of this vector, so let's put that in there. That is a length of 300. We also know that this angle here is 20 degrees. All right, so here's where some geometry comes in. So we have this right triangle here, this big green right triangle, triangle ABH. And notice that that right triangle and this right triangle share the angle H. They both have angle H. And they're both right triangles, right? That's 90 as well. Well, if they both share angle H and they share a 90, that means they must be similar triangles. They must have the exact same angles. In other words, this angle has to be 20 degrees as well. Oops, not 30, 20. Right? That angle has to be the same as that angle. And that's really what's critical for this problem. Now, we're not actually going to use this small triangle. We actually want to use the bigger triangle. So we do want to know that this is the same as that, but the triangle we're interested in is this one. Our goal was to find this length here. We have this length, and we know that that's a 20-degree angle. So to solve this, all we need to use is regular trigonometry. This is a right triangle. I have the opposite side, and I'm trying to look for the hypotenuse, right? The length of this is the hypotenuse. So we need to use sine. So sine of the 20 degrees has to be opposite, which is 300, over hypotenuse, which is the magnitude of F1. All right, that's all it is, just right triangle trigonometry. Sine of this angle is opposite over hypotenuse. And we just need to solve it for the magnitude of F1. So multiply that over. Divide by the sine of 20. Put that in your calculator. Make sure you're in degree mode. It should be approximately 877 pounds. And that's it. That is the weight of the piano. Now, if you wanted to go back and find the weight, like the amount of force that's pressing on the ramp, then what you could do is you can represent this vector as the sum of these two vectors here. If you take this force plus the force that you're pushing the piano up the ramp, that is actually equal to this vector that you see here, and then you just find the magnitude of that vector. Or you could use right triangle trigonometry as well. Since we know this is 877, you could use Pythagorean theorem, or you could use right triangle trigonometry to find this one. Okay, hopefully that's enough for that one. Let's go to our last one, and this is probably the messiest of them all. Okay, so in most of our problems, it's not always stated, but basically all of our problems are going to be in what's called static equilibrium, which means that the object is not actually moving. The object is stable. This actually applies to this previous example as well. It's incorrect to say that we are actually pushing the piano up the ramp. It really changes the math involved in the problem. What we're really saying is that we are pushing against it and it's not coming back, meaning it's in static equilibrium. There is a force here that is counteracting the force of it pushing down, and they're just equaling out. That's really what enables that problem to be done. So almost all of our problems will have this property. If that's the case, then what has to be true? For it to be in static equilibrium, the sum of all the forces have to add up to 0. The resultant of all the forces has to be 0. All right, so that's what we're going to use to solve this problem here. So what we have is a box of supplies that weighs 1,200 pounds. It's suspended by two different cables, and they're attached at different angles on the ceiling. So one's attached at a 30-degree angle, the other one's attached at a 45-degree angle. Now, just using our knowledge from geometry, that forces this cable to be longer than this cable. We know that in a triangle, the bigger the angle is, the longer the side opposite that angle. So this cable would have to be shorter than this cable. Okay, so the fact that these two angles are different means that the forces on each cable, the tension in each cable, is actually different. Okay, so what we're supposed to find is what is the tension on each cable? What's the tension, the force being applied here and the force being applied here? So I have to assign some variables. So I'm choosing F1 and F2 to be the force vectors on the cables. And obviously this would be the magnitudes. And we're going to let F3 be the force of gravity, pulling the object down. So I've kind of represented the same picture here. The thing that you can't read into is that the lengths of these vectors do not correspond to the lengths of these cables. The length is representing the tension in the cable. And for right now, they're arbitrary lengths. I mean, I did make them the correct length, but you wouldn't know where to put it in general. Now, what we do know is, given the angles in the figure, the original angles, we can use that to solve for the angles that you see here. So, for example, I put the 30-degree angle here, which means that this angle would be 150. Obviously, that one's still 45. So this enables us to write down the formulas for each of these vectors. Let's start with the easy one. So I've placed this point right here at the origin. So the easy one is the force vector for gravity. So F3. So F3 has to be the vector negative 1200 J. Right? It's got 0 horizontal component. It just goes down to 1200 on the y-axis there. So that one's easy. Let's do F2 then. So F2, again, the way we're going to do this is the magnitude multiplied by the cosine of its direction times I plus sine of its direction times j. All right, what we don't know is the magnitude. So that is actually the variable in this problem, and that's actually kind of what makes it messy, is I just got to keep writing this, and it gets to be a pain. All right, we know the F2, we know the direction is 45, so this is cosine 45 I plus sine 45 j. All right, so if we simplify, we get this. And we're not going to distribute that. We're just going to leave that out in front. Maybe later we'll distribute, but it's just too messy for now. Okay, so we'll do F1, going backwards here. So we need the magnitude, or sorry, we don't know the magnitude. Again, that's what we're solving for, so we'll leave that as a variable. And then we can go straight to cosine of the angle for this one is 150. I plus sine 150 j. Alright, so then simplifying that one, if this angle is 150, then the reference angle is 30, so the cosine is going to be radical 3 over 2. And then the sine will be 1/2. Oh, sorry, forgot my negative. It'll be negative because we're back here. Negative radical 3 over 2. Sine will still be positive. Okay, so we have all three of our vectors represented. So the next part is where the static equilibrium piece comes in. So we're assuming the object is not moving. It is actually hanging there, which means all the forces have to cancel out. These three forces added together have to be 0. And you can actually see that in the picture. So the way to see it is if I take this vector and bring it down here, and then I go back and do the other vector. Let's actually do a different color. That's going to be too fat. And then add it on here. So you can see the three vectors being added. F3 plus F1 plus F2 takes me right back to the starting place. I started here, and I traced it out, and I ended up back here. The three vectors add to 0. So that's what we mean by static equilibrium. Over here is the same thing, I just added them in a different order. I did F3 plus F2 plus F1. Still got back to the same place. So it doesn't matter what order you add them in, you get the 0 vector no matter what. It's in static equilibrium. So that's what we want to write. We want to come back here, and we want to say the three vectors add up to 0. So F1 plus F2 plus F3 equals 0. Actually, I'm going to put the 0 over here because we're about to write all those vectors in there. Okay, I'm going to pause you for a second so that you don't have to watch me write this out really slowly, and I'll have you rejoin me once it is written out. So we'll be right back. Okay, so there we have it. F1 plus F2 plus F3. So now we need to simplify this. So this is where we're going to group together everything that has an I and a J. So again, I'm going to go ahead and pause it. I'll do that, and we'll come back and look at it. So the idea is, you're distributing these and then grouping together all of the appropriate terms. So we'll be right back here. Okay, so what we've done is group together all the I terms. So you can see this first one is sitting here. This is the second one sitting there. There is no I term from that one. Then the J terms, when I distribute this, we would have that term, and distributing this one to this term gives us that, and then we have the minus 1200. And we've just pulled the I and the J out of those. So this is the A value if you want, and this is the B value, the horizontal and the vertical components. Now they are equal to the 0 vector. So this is not just your regular old 0. What that really says is 0i plus 0j. That is what the 0 vector is. The only way that can be true is if this is equal to 0 and this is equal to 0. So let's write that out. Again, we'll pause you for a second. Okay, so again, this was the 0 vector. So this A component has to be 0, the B component has to be 0, so we've just set those two equations up. Oh, and I see I forgot to put in my norm of F2 here. Right, that should be behind this term here. Now what you actually have here is a system of two equations with two unknowns. Just a regular old 2x2 system. We can solve it using elimination, substitution, or matrices if we wanted. So the first thing we would do, though, is move this 1200 over to get this guy. So now, this is because it's set up so nicely and these coefficients match, I will just subtract the 2, and the F2s are going to cancel. So when we subtract down, we're going to get negative radical 3 over 2 minus a half. That is the coefficient of the magnitude of F1. These cancel, and then when I subtract down here, I'd have negative 1200. So then we can just divide this over. So we get, let's actually scroll. These already have the same denominator, so I can just go ahead and write it as a single rational expression. If you just needed a decimal, you could just plug that in your calculator, but let's clean this up just a little bit. We can get rid of the compound fractions by multiplying the top and the bottom by negative 2. I'm doing a negative, so it'll cancel out all these negatives that you see here. So again, this step would not have to be done, but this will turn into 2400 over radical 3 plus, oops, sorry, not plus 2, plus 1. All right, because these canceled right here. All right, let's just double check that. Yeah, so that's good. Okay, so if you enter that in your calculator, that comes out approximately to 878.5. And this was in pounds. So this was the force on the first vector that we had, force on this one. That's how many pounds of tension are in that first vector. So you can see it's the vast majority of it, because it was a 1200 pound box. Most of it is in that vector, or in that cable. Okay, so to get F2, just like we would with any normal system, we need to take this expression and plug it back into either the original or into this equation here. What I think that I did, though, when I did this by hand, is I actually rewrote this before I plugged anything into it. I just went ahead and added this to the other side. So that would turn into, and I'm going to flip it around too, so this actually looks like, let's leave it actually the way it is. So radical 2 over 2 magnitude of F2 has to be equal to radical 3 over 2 times the magnitude of F1. Just reordering that equation, just adding that to the other side. And then we could multiply both sides by 2, or just multiply by the reciprocal of this, really, which tells me that the magnitude of F2 is equal to 2 over square root of 2 times radical 3 over 2 times the magnitude of F1. And those 2's cancel, so it's really just radical 3 over 2 multiplied by this thing here, multiplied by 2400 over square root of 3 plus 1. So that would be the exact value. Approximate value comes out to, oh, that doesn't seem to make sense, does it? That comes out to 1,075.9 pounds. Okay, so that seems strange. Why does it seem strange? Well, the box only weighed 1,200 pounds. So how are we getting tension? Total tension is adding up to more than that. Well, I'm not a physics expert, but the more I think about it, actually, that does seem kind of reasonable, because you're going to have these two cables pulling against each other. As this cable is pulling back in this direction, it's actually applying some force onto this cable as well. So it seems strange, but it looks like the total, if you just kind of added those forces up, the magnitude, I should say, if you add the magnitude of them, you're getting more than just the weight of the box itself, because the cables are actually working against each other as well. So, but that completes the problem. We were just asked to find how much tension is in each cable. So you had 878.5 in the one on the left, and 1,075.9 pounds on the one on the right. All right, there's a long set of notes. Hopefully the future ones don't continue to being as long as this one, but good luck on the homework. Make sure you're emailing me if you have questions, and we'll see you at the next one.